Example 2, we've got a mass spec, an IR, and an NMR. Solve the structure. If we start with the mass spec, we can see from here, 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 and even here, without even looking at the numbers really, that we've got a bromine in the molecule. See the peaks 2 units apart, equal intensity, bromine. Then if we look at the mass of the highest mass per charge ratio, we're looking at about 180, let's say, over here. That would be bromine 79, and 182 over here, that would be bromine 81. So the molecular weight is around 180. So if we look now at the IR, there's a carbonyl. I can't tell anything else for sure. There may be other information, but I can't tell anything else for certain. So let's look at the NMR, and I'm looking now at the red lines here. Those are going to be my integrations. So if I think about the integrations and the multiplicity, we're looking at a triplet and a triplet and a triplet and a quartet. And to get the integrations, I want to think about the relative size of these integration increases, and it doesn't take too much thinking or counting, right? If you measure that distance or that distance, that it's 2 to 2 to 2 to 3. So my integrations are 2 to 2 to 2 to 3. So now if we try to determine some structural features from this, well, I've got a triplet, or rather a quartet. That means it's split by 3 equivalent protons. And I've only got one peak that is integral, that has a multiplicity of 3 in terms of the relative ratios of the integrations. So it's likely that these go together. And so that seems like that's an ethyl group. So I've got an ethyl group that is a structural feature. And that leaves me with these two that would be splitting with one another. They integrate also, each for 2 protons, so at least to start, that seems like that's an ethylene unit. So taking everything together now, it looks like I've got a bromine, a carbonyl, an ethyl group, and an ethylene group. So let's put our pieces together in a way that preserves them as pieces. So start with the carbonyl. It's got 2 attachment points. Maybe put our CH2CH2 here and our ethyl group here. There's only one place left for the bromine, so that's it. So how about this structure? Let's check it to see if it works. It's got all of the pieces. It's got a carbonyl, a bromine, and then each of our proton containing pieces. This would be a triplet split by these two. That triplet would be shifted by an electronegative group, so I should have a triplet that integrates for 2 at around 3.5. Sure enough, I should have a triplet now that integrates for 2 that isn't quite as far downfield, maybe more like 3. I have that too. I should have a triplet that's not very far downfield that integrates for 3. I have that. And then I should have a quartet. And I have a quartet. You might say, well, the chemical shift for that is wrong. And if you notice that, that's great. Then you're doing what you're supposed to be doing. But let's say we didn't notice that. And we say, well, all right, this works in terms of the integrations and the splitting. So what's the molecular weight of that? So we're going to add up all of the atomic weights, and what we're going to get is a molecular weight of 164. And we saw that we have a molecular weight of around 180, so that's not it. But if you're smart, you realize that is too little by 16. 16, that's very convenient. That's an oxygen atom. So we're going to go back and we're going to change our answer, but we're going to include an oxygen atom. So let's fix it. So we're going to start again with our carbonyl. Everything that we had written down here was okay. Up here we'll insert our oxygen atom. And now we fixed the problem that you might have noticed earlier. This is supposed to be a quartet, and it should be shifted at downfield to around 4 parts per million, but it wouldn't have been in this structure. It is now. That's a better match. The molecular weight for this, if I use bromine 79, is 180. That's it. That's my molecule. That's my answer.